Hello, welcome. My name is Eli. This is going to be our first lecture for AMAT 112, first course in calculus. Let me share my screen and then we can begin. Hold on. Actually, I need OneNote open also. Okay. Okay, so in this first video, we're going to start in chapter 1. And we're going to introduce functions and sets. And these are perhaps the most fundamental, important concepts in all mathematics. I mean, really all modern mathematics is about it's about talking about functions, talking about sets, describing them, deducing properties about them. In mathematics, every question in one way or another comes down to a question about functions and or sets. So these are very important concepts, and they're very natural concepts too. They're not just these abstract concepts that mathematicians think about only. So scientists, for example, chemists, physicists, biologists, these sorts of concepts also come up in those areas, especially more theoretically oriented branches of the sciences, especially, for example, physics or chemistry. So these are they're not just something that only mathematicians think about. They're very natural concepts. The way we're going to introduce a function as in a set is going to be abstract, but it's going to capture the idea of that's used in physics and in the sciences. So we're going to be in chapter 1. So this is chapter 1. The chapter is technically called, let's not do that actually. Let's say chapter 1, functions and models. So I'm going to kind of jump around, I guess. Let's see. I guess we're going to be in 1.1 for now. I might skip 1.2, I'm not sure at the moment. Before we talk about function though, let's talk about a set. So there's not really a whole lot to say about a set. It's really just what you think it is. It is. So a set is a collection of objects. And so here's just different terms we might use for the same thing. Objects, elements, or even just more vaguely things. So a set is just a collection of objects or elements. So you have this, and this is of course being somewhat vague because I mean, what is a collection? What is an object? What is an element? Um, but we're just going to work with a more intuitive idea of a set. And for the most part, we're not going to run into any troubles. Um, so, naive view. So that we're taking a naive approach. Let me say that we are whoa, taking a naive approach. It's actually come to be known as naive set theory. So a naive approach to set theory. I don't know why this pen is giving me trouble right now. So naive set theory. And as I said, for the most part, that's not going to be a problem. Like this definition right here, I gave of the set. It's not really super rigorous. It's not super, maybe even in that informative. It's just what you would think it is. And for the most part, this definition is going to be perfectly fine. But there are some troubles. So for example, so let me just point this out. Uh, geez, there are some troubles with this approach. I don't, what is wrong with this fucking right here? Okay, anyways. Um, so for example, there's a thing known as Russell's paradox, and I'm not going to go into details of this. It's a very important paradox in set theory. It kind of led to the development, putting set theory on a more rigorous foundation, because there were some ways of that people were trying to define a set theory, like a theory of sets, but there were some assumptions that they made, and Russell um, pointed this out with his paradox. He has many paradoxes in logic and set theory, but this is like perhaps one of the earliest ones. Um, so I'm gonna actually my hold on. I'm gonna stop and figure out what's wrong with my pen so for a minute. So just give me. So hopefully I've fixed the issue now. So let's see. I'm gonna share my screen again. Okay. So yes, we're gonna take this naive approach to set theory, and a set is just going to be a collection of things. And typically, this would just be sets of numbers. But as you go along and further into mathematics, you'll see that sets become much more complicated, and that you're not really just thinking about sets of numbers, but sets of other mathematical objects. So, for example, we're going to look at functions, and you can um and I'll explain what a function is, but you can look at sets of functions themselves. So you can, or you can look at sets of sets, sets containing sets or subsets. So, and this will lead to other branches of mathematics. Um, but so for us, the most part, sets are just going to be collections of numbers. And this naive approach is going to be fine for us, but I just want to point out that there are troubles with this naive approach. So for example, there's this guy, Gottlob Frege, and he noticed that there were some issues, logical issues with mathematics, and he wanted to put mathematics on a firmer foundation. So he wrote this whole work on trying to put mathematics on a firmer foundation, and Russell came along and basically destroyed his whole book with his paradox, which is, let me see, Russell's paradox here. So if you're curious about what that is and how that helped in the development of mathematics, you can look that up. There's a pretty decent Wikipedia article on it. Of course, I'm open to discuss it with you at any point. So this is going to be a set, and it turns out we can put a sort of arithmetic on sets sets. Let's see, actually, maybe I want to say, um, before I talk about arithmetic on sets, here's some just more notation. So I'm not sure exactly how much this is going to come up, but this notation right here just means it's just a symbol for the empty set. The set with no members, no elements. That's another word right here I can put in. Members. The things belonging to the set are members or elements or objects. And the empty set is the set with no members, no elements, no objects. Um, the empty set is a thing, though. It's not nothing. The empty set still is a thing. It just has nothing in it, no thing in it. So here's some other notation. If so, let's say if A and B are sets, whatever, sets of numbers, sets of colors, um, sets of holidays, whatever, it doesn't matter. If they're sets, then the notation, this right here, I'll put in quotation mark, means that A is a subset of B. And that may be another way of saying is that is every element of A is an element of B. But not vice versa, of course. You could have what you would call a proper subset of B. So another way of saying that, i.e., if actually I don't want to say these, just that yet. All right. So hopefully it's clear what a subset is, and this is just notation for that. Just means that A is a subset of B. Um, and here's some more notation. If X is an, let's not use X, let's say A. If A, no, that's terrible too, because then it's not. Let's stick with X actually. If X is an element of the set A, then we write X in A to denote this. So this just right here, this notation means X belongs to or is a member of. That's all that means. X is an element of A. It belongs to it. It's a member of it. It's an object in it. These are all just synonymous ways of saying the same thing. So this is just more notation. So hopefully, you shouldn't be too frightened by this. It's just notation. And honestly, that's a lot of what mathematics is just getting used to this new notation. Mathematicians don't contrive or design this notation to confuse, but actually to make things simpler. So when you see new notation, there's nothing deep about what's going on. It's just mathematicians are lazy and they don't want to have to write this all the time. So rather than writing this all the time, X is an element of the set A, we just have this shorthand because mathematicians are lazy. And they have better things to do, I guess. I don't know. Anyways, so this is just more notation. Um, and I think with that, we can actually describe the arithmetic on sets now. So arithmetic of sets. Um, so let's say given A and B as subsets of, let's say, capital U, or not capital U, yeah, whatever. Anyways, U. Um, so I want A and B to be living inside the same big subset. So there's this large set U, and A and B are subsets of U. So let's even use our notation. I.e., A is a subset of U, um, and B is a subset of U. I need to assume that A and B are in some common set use in order to make sense of the following. Then I can define union and intersection of sets. Um, and so the union and intersection are going to be new sets, and so I need to describe their elements. So um, I'm gonna actually I forget there is this notation I'm gonna introduce also simultaneously. It's called set builder notation. Um, Probably should have done that first. Um, but it's not that hard to follow. So the union, so given these sets A and B, their union is denoted by A cup B. And it's, the union is just what you would think it is. So it's everything in A together with everything in B. You just collect everything together in one larger set. So it's denoted by this. So let me redo this right here. So A union B. And so now I have notation, right? And I just said in words how you define it, but let's express how you define it in mathematical notation. So here's the notation, and here is how you define it. Is denoted by and is defined. or let's say as following. So the union is the same thing as, and here is the set builder notation, the set of all x dot such that x is in A or x is in B. All right, so typically we use these like curly brackets, these braces right here, to denote sets, and then anything between them are the elements of the set. So this is the set. So how do you read this? Set of all elements x, and then let me shift this over actually because I need a little bit more room. So this is going to be read as a set of all elements x, and then the colon right here is read as such that, and then the condition is x. So x belongs to A, or x belongs to B. So a lot of words to express something very simple, and that's why we use this notation right here. Because we're just want to we use this notation um to describe this set here right here. Instead of using this natural language here right here as the set of all elements x such that x belongs to A or x belongs to B, we just use this simple notation here and it conveys that idea. So again, how do you read this equation right here? Well, you have these curly brackets right here, and that denotes that we have a set, and it's the set of all x. So x is just some stand-in variable. It doesn't have to represent anything in particular. It just represents some element such that, and then these are the conditions right here that the element x has to satisfy in order to belong to the set. So that's the intersection and the union, and then I'll recap on set builder notation. I should have started with that, but I will end with a recap on set builder notation just so it's clear. Um, so sorry, that is the union, and now we want to define the intersection. The intersection is denoted by a, like, I don't know what you would call that, but anyways, it's that. So it's denoted by this. And so we have some notation for the intersection, and now we actually need to find what is it. So and is defined as, well, intuitively we probably can figure out what the intersection is. It's like the overlap of the two sets A and B. It's everything in A and everything in sorry, it's not everything in A, it's the common elements. So an element belongs to the intersection if it belongs to both of the sets, right? So how do we express that mathematically? Well, let's try to take a crack at that. Well, it's going to be some set, so we have to use our curly brackets, right? Well, it's going to consist of all elements x such that, so all the elements x, and then this is the condition. So now I want to state, what does it mean to belong to the set? Well, x belongs to this if and only if x is in A and x is in B. Notice the difference here. The union is or. You don't have to belong to both. You could just belong to one or the other. You could belong to both. That's very possible. Or doesn't exclude you from belonging to both. When you encounter an or statement in mathematics, it just means, well, in order for the or statement to be true, you just need for one of the conditions to be true. So if you belong to A, then you're gonna belong to the intersection. If you belong to B, you're gonna belong, sorry, the union. So let me start. If you belong to A, you're gonna belong to the intersection. The union. If you belong to B, you're gonna belong to the union. If you belong to both, well, you belong to at least one, so you belong to the union. So or in mathematics is not used in an exclusive sense. Usually in sometimes in natural language we use or to like present exclusive alternatives, like things that can't both be the case. But that's not how we use or in mathematics. So or can mean both. So no, yeah, again, for union, it's or X belongs to A or X belongs to B. And for the intersection, it's X belongs to A and X belongs to B. So again, so all the elements X such that, again, remember these dots right here, these colon should be read as such that, and then everything following the colon are the conditions that this element X has to satisfy in order to belong to this set. So let me just recap. Let me just I've already kind of used set builder notation, but let me just give a more general introduction to set builder notation. And again, we're kind of taking this naive approach to mathematics. So I'm going to kind of make an assumption here, and for the most part, it's going to be perfectly fine assumption to make. So given a set A, so if I give you some set, um, it's going to assume it's not the empty set. Let's because we don't want to talk about the empty set, but let's say it's non-empty. It has objects, and in order to belong to the set, your objects have to have certain properties. So for example, you can talk about the collection of red things. And so the property, so we could say A is the set of red things. So in order to belong to the set, you better be red. This thing better be red. The object better be red. Um, and if the object is not red, it does not belong to the set. So given a set, we can say that there are a list. Maybe the list has just one um the list might not be a true list of things. It might just have one statement in the list, which is fine. There is uh there is a list. There is a list of properties, or sometimes you use the word predicates. So properties or predicates, if you're into philosophy and logic. Um, but they basically mean the same thing. Properties or predicates that an object X, say an object X must satisfy or have, so it either has to satisfy these properties or have these properties, like have the property of being red. So A could be the set of all red things, and if you have the property of being red, you belong to the set. These properties in order to belong to A. So there's going to be this list of properties. So really, it's going to be like a bunch of statements. So like you have statement one, statement two, and we can just call it our propositions, even statements or propositions. So you could have proposition one, and you could call it P1, proposition two, P2, proposition three, P3. And so in order to belong to this proposition that you assert about X has to be true. So P1 has to be true about X, and P2 has to be true about X, and P3. So I have like you have all these statements and you have ands, the and between them. Um, so I'm kind of like brushing under the rug also some ideas in logic where you can take propositions and you can take the conjunction of them, and that's just saying, so propositions P or in proposition Q, you can take their conjunction P and Q, and that will have certain truth values. Just the usual, it would be the truth values that you would expect. So we can list, so if we have this list of properties that X must satisfy in order to belong to A, we can just give it a name. So let P be the list, or this list of properties, and let P of X um be the proposition or statement that X has them, has these properties. Now, X might not have them, but you can still make the assertion or the claim, and then it's up to you to determine whether X does in fact have them. So, for example, P of X could be, so for example, P of X could be the statement X is red. And you can take X to be a given thing, like the ball in the yard, the ball in the backyard. So X is the ball in the backyard. The ball in the backyard is red. Now it's up to you to determine whether it's not true or not by go and observe the ball and observe whether it's red or not. So you have this proposition, and in this case, there's not really a list, it's just one property that you have to satisfy, and then you can select all the things. So now A would in this case be the collection of all things that satisfy this proposition. So we can use so in this case, A is the set, not necessarily X does, P doesn't necessarily have to be this proposition anymore, but A is the set of all things, of all X, let's say of all X, such that P of X is true. It's a true statement. So for example, the ball in the backyard is red. If that's true, then the ball in the backyard is an element which belongs to the set A in an abstract sense. It doesn't literally belong. The sets are not physical objects, they're these abstract objects. So now A is the set of all X such that P of X is true, and we use the notation which we've already used to denote this. Denote this. So we could say A is the set of all X such that P of X is true. And then so basically I give you an object in reality, and then you have this proposition, and I say so I'll call the object in reality X. Maybe X is the ball in the backyard. Who knows? It could be anything you want. And then I ask, is P of X true? If P of X is a true proposition or statement, then X belongs to the set. If it isn't, then X doesn't belong to that set. So that's really just the idea behind set builder notation. All right, so now hopefully that makes some sense. And with that in mind, we're using set builder notation to define unions and intersections. So you can see if I give you two sets A and B, they're going to be subsets of U. So that is, you can write it out in that way. Their union is denoted by this. So this is the notation. And how do you define this notation? Because I can't just say, here's this notation and not tell you what it means. Here's what it means. The union, A union B, is all the elements X such that X belongs to A or X belongs to B. And as I said, the colon symbol here is represent, you read that it says such that. And then in this case, this would be our P of X right here, right? It would be the proposition that X belongs to A or X belongs to B. And now there again, you have their intersection. Here's the notation, but I can't just give you this notation without telling you what it means, well, here's how you define this notation. It's going to be all the elements X such that X belongs to A and X belongs to B. So this is an example of set builder notation. All right, so I think that's enough for preliminaries on sets. Let's talk about functions now. So and throughout we're going to talk about sets again. Sets are going to come up. Sets and functions are always going to come up. So now a function is, I'm going to pull up the book in a moment just so we can look through some examples. But a function is basically a way of describing the fact that one quantity depends upon another quantity. So these you can imagine can show up very naturally. So here, let me pull up the book. Hopefully you can see this. The book has some decent examples. So functions arise whenever one quantity depends upon another. And as you can imagine, this is going to show up a lot in science. So for example, if you want to describe the, let's say, the temperature of a room, suppose you have, sorry, my computer's bugging out a little bit. Well, let's just look at these examples and then maybe I'll state another example. So here's more of an abstract sort of mathematical example, but you can imagine that has applications, of course. The first is that the area A of a circle depends upon the radius. So you have this rule that connects R and A. So these are quantities about a circle. They're numerical quantities that you associate to a circle, the radius in this area, and the relationship between these two is given as follows. A is equal to pi r squared. So what this means is that for every positive number I give you, positive number r I give you, you can associate exactly one value, and that's important. That's going to be an important property of functions. And so in this case, you can say A is a function of r. And then here's another example. These are kind of boring, I guess. Sorry. The human population of the world P depends upon time in a pretty obvious way. Or it's pretty obvious that it depends upon time, maybe not obvious exactly how it depends upon time. And that's basically the function of, or the role of science, is to find out, you have these quantities, you know that they're related, but you don't know exactly how they're related. So you develop theories, you perform experiments, you collect data to determine exactly how two quantities are related. The first one, as I said, is mathematical. You can prove. You don't have to run an experiment. You don't have to collect data and do a statistical analysis to determine that the area and the radius are related in this way. This is a mathematical fact that you can prove using logic. But this next one would be something that would be in the purview of science. You would need to collect data and do some fit the data and to determine exactly how these things depend. And there's some other ones. There's like mailing, but you get the idea. There's this. You have a one quantity depends upon the other, and the quantity is changing as the other one changes. And that's going to be another important part. That's going to be the whole project of calculus, is that when you have a function changing with, or you have a quantity that depends and changes with respect to another, you're going to want to find how does it change at any given instant. And that's basically the motivation behind calculus. So another example would be, as I was saying, you could have, let's say, I don't know, you have a room, and then you have maybe like a heat source here. So this is like a heat source. And then it's heat is distributing throughout the room, and then you can say, all right, well, I give you a point. There should be a unique temperature at that point. and it's going to depend upon how far you are away from the heat source. So it's like you have a radius. So like let's say this you have a radius to this corner or a distance from this corner, from a point in the square to this corner. And as you get closer, as you travel along this line, the temperature is increasing and as you go away from it, the temperature decreases. So in this case, so let's say a room with a heat source, and then we could say room with a heat source, we could say that temperature at a point in the room is a function, i.e., it depends upon. So that's what a function means. It depends upon. So temperature at a point is a function, i.e., depends upon um the point in question, I guess you could say. So as you move around in the room, the temperature at those points is increasing or decreasing. And there's going to be just tons of examples. I mean, it's hard to not find an example. All right, so what's the common thread between these examples that we looked at? Well, the idea is this: you have two quantities, right? And especially in the case with the circle, you have this formula, you have this rule, and you can plug in one of the quantities and determine you get an output, which is the other quantity. And then this rule expresses exactly how these quantities depend upon each other. So let's try to come up let's now write down a definition that kind of abstractly formalizes this idea. So we're going to talk about so this is a definition, and we're going to formally define a function, but it's going to capture all the ideas that we just discussed. So this is a function. So a function, and so we need some notation. So function denoted by f, so we typically use f, g, h, is a rule that assigns to each element x in a set D exactly one element. So exactly one element. And what do we call this element? We call it f of x in a set E. So we have this function. It basically, you can take a point or an element in the set D and you get exactly one output. So here's some notation. So we typically use this notation. So F colon D arrow E. This indicates, um, let's say indicates that F is a function that F is a function from D to E. So what does that mean? That means you take X in D, and that implies that F of X is in E, and this is a unique value. And then we typically call so here, so D is called the domain of F, and then E is called the codomain of F. So if we look back at our one example of the area, so A area of a circle is going to be a function from positive numbers, non-negative. Actually, we don't want to talk about zero radius. So 0 to infinity to actually this will also be area is also positive. So it's a function from 0 to infinity to 0 to infinity, and it's given as follows. You take a number, you take an input R, a radius, so this is a radius, and R belongs to the set 0 to infinity, and you get back pi R squared, if I did that right. And this is obviously pi r squared is obviously also a positive number. And notice there's exactly one number. It wouldn't make sense to, if I give you a radius, it wouldn't make sense to say that there are two different areas associated to that. Or going back to this one example here with the room and the heat source, if I give you so the inputs are going to be points in the room, the output, so let me just say that. So um, input of this function is input of this function is points in the room. And then output of this function, oops, this particular function right here is temperature. Oops. Temperature at a point. And it makes sense that we want to require our function. So in this definition here, we say we want exactly one output. So I give you an input X in a set D, you get exactly one output. The rule assigns exactly one output in this, what you call f of x, in the set E. And that makes sense that we would want that restriction based upon all of the examples we looked at. So for example, for this one, if I give you a point in the room, like right here, or maybe even right here, and then you look at the distance here, it wouldn't make sense that to say that there are two different temperatures at that point. That doesn't make sense. You can have only one temperature at a point. Um, and again, back to the area example, it wouldn't make sense if I gave you a radius that there would be two areas. That wouldn't make sense. So it's an important restriction that our functions have exactly one output. All right, so that's the basic idea behind a function. It's an abstract mathematical definition, but it has enormous applications, and it describes all the sorts of things that you would see in science. Science is always about finding relationships between quantities or things or phenomena, and that's exactly what a function describes. So here's this notation. You have this arrow notation right here. And it just indicates that f is a function from D to E. So it takes as an input x and D, and it gives you a unique output f of x in E. And then D is called the codomain of f, and D is called the domain of f, and E is called the codomain. And then some more notation. There is a set that we can also always associate to this, and it's called the range or the image. I tend to use image for reasons that will kind of be clear in a moment. So the notebook doesn't use any notation, so I'm just gonna write down some common notation. So what is the image of F? Well, it's basically gonna be the set. It's gonna be a set. So the image, let me actually write that down. Let me be a little more formal. I'm gonna write down a definition. So let me be somewhat formal. So the image of a function f, and we're gonna assume it goes from D to E, is defined to be the set IM of F. And if it's a set, I need to describe the elements. Well, I'm going to use set builder notation to describe the elements. So it's going to basically be the set of all outputs. So it's going to be all the F of X such that X belongs to the domain. So it's pretty simple definition. Might be a little confusing at first, but it's basically how this is how you build the set. You take an element X in your domain, then you plug it into your function, and then you put it in the set. And then you just keep repeating this for all the elements in your domain. So I think probably in a moment we're gonna look at an example. So yes. So yeah, so I will write down an example in a moment. Let's see. So far, all right, so some more notation and convention. So um let's say variables. So a symbol that represents an arbitrary or just non-specific, I guess maybe you could say, an arbitrary or non-specific or general, etc. Element or element in the domain of a function is called the, or so let's say, and called, sorry, got a lot of windows open, so it's kind of lagging a bit. So the symbol itself is called an independent variable. So like a typical symbol we use is um X. And then a symbol, oof, this is a lot to write. A symbol, let's say representing a number, well, let's not say number, but just element more generally. An element in the range or image, oops, the range or image of F, the function F is called a dependent variable. Oof. All right, this is not working very well. So it's called, so the symbol is called called a dependent variable. So you have a symbol that represents an arbitrary element in the domain is called the independent variable. And the symbol representing an element in the range or the image is called a dependent variable. And I should note, I didn't note this above, so recall that the image of F or the range um, which is defined as this, is a subset of E. And that's because if X is in D, then by definition of a function, F of X is in E. So these outputs right here, they all belong to E So the image is a subset. Hence, we can write the image of F is a subset. Now, it's important that this is can be proper. A proper subset can be a proper subset, meaning that there could be an element in E that's not in the image, and that's actually can happen a lot. And we'll see some examples. So let me see. Maybe we want to just look at an example right now. Yeah, let's do that. So let's do an example. So let's say we have a function f and it goes from R. So we're going to basically mostly look at our sets are going to mostly just be real numbers to real numbers. Actually, before I do this, I didn't really, so I just wrote down the definition of independent and dependent variable. But let's look back at our example to kind of make sense of this. So and for this example, um, R is going to be the independent variable. And then A is going to be the dependent variable. It depends upon R, and R doesn't depend upon A. So this R is the independent variable, is the dependent variable. All right, so there's that. All right, so now let's look at an example to kind of tie everything together. So we have F is a function from the real numbers to the real numbers. So I'm telling you the sets, it's a mapping or a function between R to R, but what's the rule? Well, it's going to be um x squared. So let's look at the image. So what is the set of all outputs? Well, we know that if x is a number, then when you square it, it's always going to be positive, right? No matter what. But f x squared just is f of x, right? So this says, hence, the output of f is always non-negative. So it's not hard to see. There's another half of the argument, but I'm gonna just leave it out, that the image in this case is this set, right? 0 to infinity, including 0, because f of 0 is 0. And this is a proper subset of R, right? There are elements in R that are not in this set here. Just take -1, for example. So it's a proper subset. So here's just some ways of visualizing a function. I'm just going to pull the book up here for a moment. So you can imagine it's like a machine that you have this X as your input, and then the function itself is the machine, and you pass this input through the machine, you get this output. So I mean, if that helps you, it helps you. If it doesn't, that's fine. Sometimes these like pictures and these analogies and these metaphors are helpful, and sometimes they're not. So if you like metaphors, analogies, pictures, diagrams, then by all means, reflect on these sorts of things. But if not, just you can just take the definition of a function at face value and just be like, this is the way functions are defined. I don't need pictures to understand that. That's sort of more or less how I work. I don't really operate with pictures and stuff like that. So here's another diagram. So you can imagine like F, you have this arrow diagram for F. So you have this set D, and you can imagine that D is just, well, it's just some set. You don't know exactly what it is. Um, it's just like some blob right here. And you have like these points, and then you have some set E, it's some other blob, and it's meant to be vague in this way because These sets could be anything. They could be real numbers, in which case D would be a real line, it'd be this arrow pointing to positive and negative infinity, or this line, infinite line, and then E would be also. But it can get more complicated. So for example, you can have functions, well, like for example, the temperature, the function would be the domain in that case would be the plane, right? Because you're talking about points in that square. So it would be a subset of the plane. And then it sends a point in the plane to the real line, which is you interpret as the temperature. So, these pictures, your functions can be defined in very high dimensional spaces. In fact, the function you can when you go later into mathematics, you'll look at functions on infinite dimensional spaces. So there's just no way of representing it really other than as some abstract blob that's kind of representing what's going on. But thankfully for us, we're just dealing with calculus, calc one, and so we're looking at functions of a real variable, so everything can be visualized very nicely. All right, so let's see what's next here. And speaking of visualizing, this is a nice segue actually. Um, we want to, so we've associated one set already to a function, and that's this set right here, the image. Turns out there's another set. So we can talk about the graph of a function. This is another set. And this set you can actually associate to any function whatsoever, whether your function is from points in a plane to the real line, infinite dimensional space to another infinite dimensional space. It's the set of colors to whatever. It doesn't matter. It can be anything you imagine. You can still define this set, which we call the graph. But it turns out when you're dealing with low dimensional spaces like we are, the graph can be visualized very easily. So let's say given a function f from D to E, let's say the graph of f is defined, oops, is defined as follows. So here's the notation we use, graph of f, and it's going to be a set. So I'm going to use set builder notation to describe the elements. So it's going to consist of ordered pairs. So this is an ordered pair. It consists of all the ordered pairs x, comma, f of x, where x belongs to the domain. So basically you take a point in the domain of f, d, you plug it into the function, you get this output, and you pair it with x. So it's like you're pairing the inputs with the outputs. So pairing inputs with outputs. Oops. And as I said, when D and E are subsets of R, we can easily visualize things. We can easily visualize the function f. So let me open the book up again. So basically the idea is, so if D and E are subsets of the real line, or just take D and E to be the entire real line, you can set up two like perpendicular or orthogonal copies of the real line. So you have the one copy right here that's called the x-axis, one copy of the real line here that's called the y-axis, and then the x-axis is your inputs, the things you plug into your functions. or some subset of the x-axis. And then your y-axis is the outputs of your functions, and that's what we have here. So here's like the domain and the range, and then the height of the function from, so the height of the curve to the x-axis, that's your output of the function. So we can very easily visualize things. So let's see what's going on with this example here. So the graph of a function f is shown. Find the values of f1 and f5. You just look at f1. It's here, so it's like 1, 2, 3. So yeah, one is f1 is 3. f5, so 1, 2, 3, 4, 5. Wait, 1, 2, 3, 4, 5. I don't know. It's yeah, it's negative because it's going below the excess now. So I guess it's approximately negative 0.7. And now, so we have the domain is everything from, it's defined from 0 to 7, because that's kind of where the graph cuts off. Now, what's the output? What's the range or the image, as I've been calling it? Well, to get that, you sort of basically take the curve and project onto the x-axis. So like you look at maximums and minimums. So we have a maximum point here, and we have a minimum point here, and then you project onto here. So you get here, and that's like 1, 2, 3, 4. Okay. And then you have 1, 2, and you project that down here, down to 2. And notice there are no gaps, there are no holes in the image. So, I mean, in the curve. So every output is obtained, right? So that's why the range of the image is this whole set. Now you gotta be careful though. So let me show you that again, just because maybe I'm going a little fast. All right, so hopefully you can see what's going on here. You got to be careful though if there's a gap in your function. So let me try to make an example here. Um, so let's say you have, can I put an axis? Yeah. All right, I don't know how well this is going to come out, but let's see. So let's say you, whoops, I did not want to, anyways. Let's say you're graphing between like A and B, and then maybe like C and D, I guess. C and D. And then there's this point right here, E. So now the curve, say it looks something like this, and then, oh, there's a circle, there's a gap, there's a hole in your function, and then it kind of goes up like this. If you did the projection trick in this case, like, okay, so you can project down to here and you get C, and then you project down to here, you get D. You can project all these points, and you see you're going to fill in most of this interval from C to D, except this point right here. So if this is our function f, in this case, the image of f, or the range, is going to be the interval from C to E, um, parenthesis, union E to D. Because you can't, this point right here, E is not an output because you have this hole here. So you have to be careful when finding the image. Most of the time, though, we won't have gaps or holes like that because we're going to deal with what are called continuous functions. So we're not going to have much of an issue there. All right, let me see. Let's see. All right, so we kind of went over example 2 already. Let me see for a moment. Let me stop sharing for a second. Okay, so in this section, I'm gonna just work through an example or two, and then we'll be done with this section. There are more examples, but I'll let you work through those on your own. And of course, if you have questions, feel free to email me, and we can meet and go over them. All right, so the next one I want to go over is example 3. Okay, so this is going to be a very important example, and one we're going to see again in one shape or form. So we're going to take a function from R to R, and it's going to be defined as 2x squared minus 5x plus 1, and then we're going to take h to be non-zero but small, meaning the absolute value is small. So now what we want to do is we want to evaluate what's called the difference quotient, and this is going to be a very important quotient. It's going to allow us to define the derivative later on. So this is the difference quotient. I guess you could say it's the difference quotient at A. So let's say at some number A. And it's well defined, notice, because A plus H is also a real number. So you can plug it in. You can plug A plus H into the function. It's well defined. So how do you evaluate this? Well, it's not that hard. So we're going to take the rule for F, and wherever we see X, we're going to replace it by A plus H. So we're going to get 2 times A plus H. Oops. Yes. Sorry. It's lagging. So it's 2 times A plus H squared minus 5 times A plus H plus 1, and then minus f of A. And again, to evaluate f of A, you just look at the rule for f and replace x by h. So it's going to be minus 2a squared, and then minus 5a, so plus 5a, and then minus 1. And then all that is divided by h. So now we're gonna FOIL. So we FOIL this term right here, and then multiply by 2, so we get 2a squared plus 4ah plus 2h squared minus, and then distribute this, so we get minus 5a minus 5h, and then we have 2a minus 2a squared plus 5a minus 1. So oops. And then that's all divided by h. So now we can simplify. So this cancels with this, and then we have 4ah. Nothing cancels with that, so we can write that down. And then we have a 2h squared. That's the only copy of that, so we just write that down. And then we have a 5a and a negative 5a and a positive 5a, so they cancel. And then we have a 1, which I dropped, I guess. This should be a plus 1 right here. But that plus 1 cancels with this negative 1 right here. And then all we have left is minus 5h divided by h. And then you can cancel, so you get 4a plus 2h minus 5. All right. So let's see what's next. All right, so the next thing I want to know is this is kind of like, it's not entirely related to what we've been doing or what we just did. But sometimes, let's say, sometimes you'll be given the rule of the function without the domain. So this is, in a sense, you can think about this as a sort of like a partial function. So you're given the rule of the function without the domain. And you need to work out the domain. So for example, let's see, example 6. You could be, so this is part A. I could give you this rule, f of x is equal to square root of x plus 5. And the idea is, what's the domain? We're going to make a convention. We want it to be the largest set of numbers for which this rule makes sense. So now you can't take, so clearly you can't just take domain of f to be R. So you can't take the domain to be that large because f of, say, -6 is going to be square root of -6 plus 5, which is square root of -1, and that's no good. Can't do that. Can't take square root of a negative number, in this course at least. So we have to be a little more careful. So, so here's some convention I just stated. So this is going to help us determine what's going to be the domain. So we want the domain, and this is going to be true more generally, not just of this example, but we want the domain to be the largest set of let's say real numbers. Okay, we're always dealing with real numbers, so let's just, no point in putting it in parentheses, and no point in saying not real. So we'll just say it's the largest set of numbers for which the rule, let's say, makes sense or is well defined. So we can't use all of R because if, in this case, because if you can take -6 and you get square root of -1, so it's not well defined. In this case, you're just going to require that x plus 5 is non-negative, and then you can solve this as positive. So then you can solve this inequality. This is equivalent, actually. These are equivalent, so you can go back and forth. And that's going to imply that the domain in interval notation, f, is the interval -5. Sorry, it can be greater than or equal to. It can be. You can plug 0 into the domain. I mean, you can plug 0 into the square root. So it's going to be -5 to infinity. So f is going to be a function from -5 to infinity of going into R. Now you could also ask what's the image, and the image is going to be, the image should just be, I'll leave it to you to think about this. The image should just be 0 to infinity. The square root is always a positive number. And in fact, you can get every positive number through the square root. So let's see. And if you don't see that at all, just email me and we can work on it together. So that's A. Let's look at part B. So we have g of x is equal to 1 over x squared minus x. And again, we want to find the domain. What's the domain? And again, we want it to be the largest, we want to use this convention. We want the domain to be the largest set of numbers for which the rule makes sense or is well defined. So the only issues we get are when, so the only issue which could arise, is division by 0. So let's figure out when do we get division by zero, and then we want to exclude those points from the domain. So we'll take the denominator, set it equal to zero, and we can factor out an x, so we get x. Okay, this is kind of driving me crazy here. So we want to set the denominator to zero and find where do we get division by zero, and then exclude those points from the domain. So we factor out an x, and it looks like we get division by zero when x is equal to 0 or 1. So that means the domain, so the domain and the domain is, I'm going to describe it in two different ways. It's going to be all the x, real numbers x, such that x is not equal to 0 or 1. And in interval notation, that's going to be equal to -infinity to 0, union 0 to 1, union 1 to infinity. So basically, you got to have these two unions right here, because you want to chop up the real line at 0 and 1. So you need to include these unions to chop up the interval at these points. So that's so that would be the domain. All right. Hold on for a second. Sorry about that. I have like 5 dogs and they were all barking. Not that maybe you didn't hear them, but anyways. So let me share my screen. Okay. All right. Um, all right. So that's that example. So in the next thing we want to look at, and maybe it's one of the last things, not quite, is which functions define or which rules define functions. So if I give you a function from real numbers to real numbers, you can plot it and it'll be some curve in the plane. Um, and then you might wonder, well, if I give you a curve, so in other words, what's the flow? I give you a function, you can plot its graph, and it will be some curve in the XY plane, the coordinate plane. And you might wonder, okay, well, if I give you does the other direction work? If I give you a curve, does that does there exist a function associated to that curve? That is, if I give you a curve, is there some function whose graph is that curve? And it turns out the answer is in general no. Um, and so here, let me pull up some graphs from the book, and the answer to that question in general is going to be the vertical line test. So it turns out that we actually have necessary and sufficient conditions for when a curve corresponds to a function. So this is called the vertical line test. So it says a curve in the xy plane is the graph of a function, um, if and only if no vertical line intersects the curve more than once. And so here's a curve representing function A. Here's a curve that doesn't represent a function. And basically the idea is this: suppose you have, why is this test true? Why is this test true? Well, let's just imagine you have this kind of curve, and we want to argue. So in other words, you have a curve in the plane where there's a line intersecting at more than one spot. You might have many lines. As you can see, there are many lines that intersect more than one spot. Well, let's just imagine there's at least one spot, uh, one line which intersects at two spots. So the problem is then as follows: if you have such a line, then you have these points on the curve AB and AC. The x coordinates have to be the same. And let's imagine there is a function, right? Let's imagine there is a function. So I don't know if I can write with this because it's so let's imagine that there is some function corresponding to this curve. So so this is like you would call a proof by contradiction. So let me pull up. All right, let me pull up OneNote. So let me just get a rough graph of what's going on over here. So we have something like this. Looks something like this, I think. So we have A, B, and C, D. So we want to argue, that no function corresponds to this curve. This curve. Well, you do this by contradiction, so you say by way of contradiction, suppose there exists a function f whose graph is the curve above. Now let's evaluate this function at f of a. So on the one hand, f of a is b, right? But also f of a is equal to c, and b is not equal to c. These are different points on this line or on this curve. So this actually contradicts the very meaning of a function. Remember, a function has, if I give you an input, it has exactly one output, but this says that the input A has at least two distinct outputs. So this is a contradiction. So hence, what that means is that what we assumed at the beginning, that is there exists a function satisfying this property, that is its curve is given above. That means this assumption had to have been false. So there is no um, function whose um, graph is this curve right here, or any curve like that. So that's kind of why the vertical line test is true. So for example, um, and then you can ask this about equations, because you can graph a function and you can also graph equations. So this allows us to determine whether an equation defines a function. A function. So for example, you could have x is equal to y squared minus 2. And if you plot this, it's going to look something like um, a sideways parabola. But you can see that there are a lot of vertical lines intersecting at more than one spot. So this shows um, this equation here that I wrote down, does not define y as a function of x. Because it does not pass the vertical line test. And you can also see that too if you try to solve for y. So let's just try to solve for y. So you add 2 to both sides, you get y squared is x plus 2, and then you take a square root. When you take a square root, you have a plus root and a minus root. So the question is, do you take the plus root or the minus root? Well, there's no way of really deciding unless you just arbitrarily say, I'm always going to take the positive root, or arbitrarily decide I'm going to always take the negative root. So that's kind of why this doesn't define a function, is because given any x, you have these two, you're always going to have exactly two y's associated to it, the plus root and the minus root. All right, so that's that is a test to tell us whether or not a graph, a curve defines a or a given curve corresponds to a function, or whether an equation defines a function. All right, so the next thing we want to look at are piecewise functions. So with piecewise functions, basically the idea is you have a domain and you want to chop up the domain into different pieces. And then you want to use a different rule depending on which piece of the function you are. So that's all that a piecewise function is. So for example, you have f of x is equal to you could have something like f of x is equal to x minus 1 if x is less than -1, x squared if x is greater than -1. So basically you take the real line and you chop it up at -1, and then you use two different rules depending upon where you are on which piece you are. So we want to the example asks us to evaluate some the function at some point. So we want to evaluate at -2. Well, in order to evaluate this, we have to check these two conditions right here, and then whichever one's true, that will tell us which rule to apply. So -2 is definitely less than -1, so we use this first rule. So it's 1 minus -2, and that will give us 3. And then we have f of -1. Well, so -1 is definitely less than or equal to -1. It's actually equal, so you use this first rule again. So it's 1 minus -1, and that's going to be 2. And now you have also 0, and 0 is greater than -1, so you use the second rule. So you square it, 0, and you get 0. And then we want to plot this. And I guess I'll just pull up the book because it's just plots are not always easy to do using OneNote. So if you plot this, you get the following graph right here. So you have this closed circle right here because it's a less than or equal in this first part of the definition. So you plug -1 in here, and then you have this open circle right here because it's strictly greater than 1. Okay, so one particular type of piecewise function we're going to encounter a lot is the absolute value function. So given number a, the absolute value of a is defined as follows. It's going to be a if a is non-negative, and a negative a if a is negative. So basically, you can see that the absolute value is always going to be positive, no matter what a is, and you're basically taking the real line and chopping up at 0 into these two pieces. All right, so there's some examples there. I'll let you look through those and work through those. Um, let's see, what else do we have here? So just a couple more things, and then that will be the end of this section. So it turns out that a lot of graphs have certain symmetry, and this makes computing and graphing, sorry, a lot of functions have symmetry. And this means computing the function at values and graphing the value, the function is easier when you have this type of symmetry that we're going to look at. So we have two types of symmetry. We have even and odd symmetry. So we have a function. Um, so, so we're going to say let f go from D to R. And we also want and D is symmetric. When that meaning, what does that mean? Meaning X is in D if and only if negative X is in D. So if like in other words, if a number is in D, then it's negative also is in D. And you'll see why in a moment, why that's important. So we're gonna say that F is a function. Oops, be a function. And D is symmetric. Then F is odd, or sorry, even. We're gonna define even first. Sorry. All right, so it's even if f of negative x is equal to f of x. So in other words, it can't tell the difference between negative numbers. And though this is why you need D to be symmetric, because if x is in the domain, you need negative x to be in the domain. Otherwise f of negative x might not even make sense. So you need the domain to be symmetric. And D is odd if f of negative x is equal to negative f of x. So in other words, you can, in a sense, factor out the negative. You can factor out the negative one. So let's look at some examples. So if I give you f defined by f of x is equal to x squared, this is even. So the reason why is if you plug in negative x, you get negative x squared. And when you square negative, it goes away to give you x squared, and that's just by definition f of x. And so x squared function is even. And let's say now g of x given by g of x is equal to x cubed. This is going to be odd. Why? Well, let's compute g of negative x. It's going to be negative x cubed. And now when you cube a negative, you still have that negative behind. So it's going to be negative x cubed is equal to the negative on the outside and then cubing the x. And that's going to be equal to negative g of x. So that's even or odd. And there's some more examples. I won't go through these. You can go through them yourself. And again, if you need to work through them together, I can definitely do that. So here's a graph of an even function. You can see it's symmetric about the y-axis. That's because you have x and negative x, and then f of x and negative f of x have to be at the same height. That's basically what this condition right here says. Um, this condition says that x and negative x, when you plug them into into the function, you get the same output. They have to be at the same height. And when you have um, an odd function, so this figure right here, you plug in x and you plug in negative x. So if f of x is say here, then negative f of negative x has to be negative f of x because it's odd. So you take this distance right here and you copy that distance right here and you get that point down there. All right. Since I have this open, I'll just use the book at this point. So the last thing we want to talk about is um, increasing and decreasing. This is going to be really important later on. All of this is going to be important, of course, but some things are going to come up more so often than not others. So it's going to turn out that we're going to want to know when functions are increasing or decreasing, and this you can imagine has lots of applications. You want to know, say, when your profit is increasing and when it's decreasing. So this is going to have lots of applications. So first of all, we wanted to define what does it mean to be increasing or decreasing, and we want to define that mathematically. So here's the idea: is basically you have a function and it's defined on an interval, so it could be even defined on the whole real line, but it could be defined on some interval, like the interval from 0 to 1 or something, or -1 to -1, and it's said to be increasing on this interval I if whenever you have x1 less than x2 in the interval, then f of x1 is less than f of x2. In other words, like the height at x1 is less than the height of at x2. See, it should be, and that's exactly what this graph kind of indicates here. So these heights, the one height is bigger. And it's said to be decreasing if, again, when you have x less than 1, x1 less than x2, sorry, in your interval, it switches the order. See, now f of x1 is at a greater height than f of x2. So I don't know, there's not a picture here. But you can imagine what that would look like. So let me stop sharing. Now I think that might be it for today. I'm not sure actually. I have to check the next section.